Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I discussed that how to determine the seismic displacement of retaining wall, and then I started one example problem. I gave the soil properties and the dimension of the wall. So, now today I will solve that problem. I will determine what would be the seismic displacement. Of course, the lateral displacement of the retaining wall, which will slide along on the base of the wall. And definitely when it will slide, when the applied acceleration is greater than the yield acceleration. Okay? And so that means first you have to calculate the yield acceleration. Okay? And the Amax is given 0.45. So, this yield acceleration must be less than 0.45. If it is greater than 0.45, then the displacement will not occur. So, let us see. Now, to get that, first we have to check that what is our K critical for this particular problem. The K critical, that is 1 minus kV into tan phi f. Okay? But kV is 0, it will be only tan phi f. So, this will be tan 35 degree, so 0.7. Okay. So, it is 0.7 and we have taken 0.2, so we can apply. Now, the theta value will be tan inverse KH 1 minus kV. Okay, and this is kV is equal to 0, it will be only tan inverse KH, and KH is equal to 0.2. So, this theta value is 11.31. 11.31. Okay. So, that means for our first trial 1, we assume that AOI is equal to 0.2 G, because this KH, the value is given, KH, this is for your, that we have to determine the KOI. So, this is for first trial only. After that, we have to change, because there is no guarantee this KH, this 0.2 is your yield acceleration. There is no guarantee. So, for the trial 1, we have taken KH equal to 0.2. Okay? And KH equal to 0.2 means the AY, because here I have seen that your K is equal to AY by G. So, if I have taken 0.2, then AY will be 0.2 G. So, here AY is 0.2 G, that is for the first trial. Okay. Now, I have assumed for the first trial that my yield acceleration is 0.2 G. Let us see from the calculation it is coming 0.2 G or not. So, because now we know the theta, we know delta, we know phi, we know beta, I is equal to 0. So, these values are known. So, that means I can calculate KAE by using the this expression, and that is coming to be out to be 0.495. Okay. So, I can write PA is equal to half gamma KAE 1 minus KV into H square. KV is equal to 0. So, I can write this is half into gamma is 18 into 0.495 into 1 into 36. H is 6 square 36. So, this value is 160.4 kilonewton per meter. So, now I know the yield acceleration equation is how much? What is the equation? Tan phi b minus PAE cos delta plus beta minus PAE sin delta plus beta into tan phi b divided by W into G. Okay. Now, what is the W value? W value I have already calculated in my previous example problem, but still I am calculating it. So, W will be for the triangle half into 1 into 6 into 24 into 2 triangles plus 3 into 5, 3 into 6, 6 into 24. So, that value is coming out to be 576 kilonewton per meter. Half into 6 into 1 into 24 into 2. Okay. So, now if I put these values here, I will get AY. How I will get the AY? The tan phi b is 33.3 degree phi b. You can see this tan phi b or delta b is 33.3 degree minus here it is PA is how much? It is 160. So, it will be 160.4 into cos 28 degree plus 9.6 degree. Then again minus 160.4 sin 28 degree plus 9.6 degree into tan 33.3 degree divided by the W, which is 576 into G. Okay. So, I will get this after solving this, it will giving me the value of 0.55 G. But what we assume? We assume it is 0.2 G. So, that means what we assume 0.2 G, and what we are getting is there is a huge difference. So, that means 0.2 G is not the proper assumption. So, in the trial 2, we are assuming, we are taking the say average value, and we are assuming that our AY in trial 2 0.37 G, say that is the assumption. So, that the same way 37 G. So, if it is 37 G, so your KH will be 0.37. Okay. If AY is 0.37 G, KH will be 0.37. So, you can calculate theta value, which is tan inverse 0.37. So, it is 20.3 degree. Now, KAE, you can calculate KAE, which is 0.75. So, my PAE, that is equal to half into 18 into 0.75 into 6 square, because KV is equal to 0. So, in trial 2, so this is 243 kilonewton meter. So, that is the PAE for trial 2. Similarly, again I am calculating AY, that I will calculate, that is 33.3 degree minus, now 160 will change to 243, other value will not change, cos 28 degree plus 9.6 degree minus 243 sin 28 degree plus 9.6 degree into tan 33.3 degree divided by the W value will also not change, 576 into G. Okay. So, it will be equal to 0.49 G. Okay, 0.49 G, but we assume 0.37. So, again another trial is required. So, in trial 3, we assume AY is equal to 0.43 G. Okay. So, my KH is equal to 0.43. So, theta is equal to tan inverse 0.43. So, that is 23.3 degree. So, again I can calculate KAE is equal to 0.884 and PAE is equal to half into 18 into 0.884 into 6 square. It is 286.4 kilonewton per meter. And if I put this value again in AY equation in third trial, I will get AY is equal to 0.46 G, which is close to the assumption of 0.43 G. But you can go for another trial with, say, considering your AY is equal to 0.45 G. There you can go for another trial also and you will get a very further new value which may be slightly close to the value which I have got in trial 3. Okay, but as it is very close, so I will stop here. But if you want, you can go for another trial also. So, that means here I will calculate now, I will take my AY, that is the value we assume 0.43 G, but actually it may be around 0.44. It will be around 0.44 or 0.45 value. So, it will be around 0.44. So, but I am taking this 0.43. So, I can calculate D permanent, that is equal to 0.087 V max square A max to the power 3 divided by AY to the power 4. So, now if I put this value 0.087, V max is 38 centimeter per second, A max is 0.45 to the power cube, and there is the AY is 0.43, but there is a cube, there is A4, that means 1 G value will come into picture, that is 981. So, if you get that value is 0.34 centimeter, okay, remember that, or it is 3.4 millimeter. So, why it is so small displacement? Because our yield acceleration is very close to the A max value. Even if you go for another trial, you may get a very further close value or closer value to A max. Okay. In such case, your displacement may reduce further. Okay. So, that means this is the process by which we can determine the seismic displacement. If your AY, yield acceleration, is much less than the A max, then you will get more deformation. Okay. But here, as both the values are very close to each other, that means it is 1.44 or 0.43, another is 0.45. That's why I am getting around 3 millimeter settlement. Clear? So, this is the end of our this retaining wall discussion. Retaining wall means that your gravity retaining wall or cantilever retaining wall discussion. I have discussed about the pseudostatic analysis, I have discussed about the pseudodynamic analysis, then I have discussed about the hydrodynamic effects of pore water, what will happen, what are the forces we will consider if it is a water formed retaining structure. Okay, and then I'm solve a problem by which you can know how we can determine the seismic displacement of a retaining wall. Now I will start the last topic of this course, that is the design of reinforced retaining wall under seismic condition. Okay, so let's start that. So what are the different types of reinforced retaining wall? Here the previous cases, in the retaining wall, the load were taken by the wall itself, or the active force that is coming is taken by the wall itself. Either you can make it a huge wall, a gravity wall, where the weight will take the give you the stability, or you can provide the reinforcement. Actually, the wall will take the load, but here we will provide the reinforcement, geosynthetic reinforcement, either geogrid or geotextile, and then we can make a steep slope or the wall where this reinforcement will take the load or the stress. So, this is your these reinforcement are this horizontal reinforcement, those are placed into the soil. Okay. So, there are different types of reinforced retaining wall. Okay, I am not going in detail all these things, because if you go for any your reinforced retaining wall course, then you will get this detailed thing, but I will only concentrate that how I will do the design under seismic condition. The static part I will not discuss in detail, like I did for the other ground improvement techniques also. I only concentrated the part which is related to this course. Okay, that is the seismic design part. So, to do that seismic design part, we will discuss some static component also. So, that among these three, I will design this third one, but the design methodology is same for all three walls. All three walls design methodology is same. So, that means I will here consider these are my the third case we are talking about. So, you can see that these are the loads under which these walls are generally been designed. What are these loads? The loads are soil pressure, that means this the backfill soil pressure that will taken by this reinforcement. Then the surcharge pressure, surcharge if you construct say an embankment over this retaining wall, say, or there may be so surcharge that is called dead load surcharge, and then the live load pressure will come. So, this is your soil pressure, surcharge pressure. Sometimes this surcharge pressure can be the dead load surcharge pressure and equivalent live load surcharge pressure. Okay. So, and or you can provide the wheel load or the point load as the line load, and you can you know these are the distribution. This is for the soil pressure. Soil means this backfill soil, soil own pressure. This is the external surcharge pressure, UDL, that distribution. Lateral load I am talking about, lateral earth pressure distribution, and this is for the point load. This is the distribution. So, overall total pressure is this one. So, as I mentioned, either you can provide the point load as a live load, or we can provide the equivalent live load as a surcharge. So, in my example problem, I have considered the surcharge for live load as well as dead load. Okay. So, now these are the loads, and you can see now what are the things you will design when you will design this reinforced retaining wall. The one is the length. What would be the length of this reinforcement, and what would be the spacing of this reinforcement. So, I will design or determine what is the L, which has two components, LR plus LE. What is LR? So, suppose this is your wall and these are the failure line. Okay. So, this is actually the failure mass and this is your failure line. So, this angle is 45 degree plus phi by 2. We are using the Rankine's theory. So, this is 45 degree plus phi by 2. That means this LR is the length that is must required within the failure mass. So, that is called LR. And what is LE? Suppose when there will be a failure will occur or soil will try to fail along this failure line. So, what will happen? It will try to fail, and if you provide a sufficient length of the reinforcement, and so that means this reinforcement will act as an anchor. It act as an anchor because this reinforcement is inserted into the soil, and when there will be a pull is applied, so there will be a friction between the reinforcement and the soil. So, those friction will give a resistance. So, that because of that resistance, the soil will not, this reinforcement will not allow to fail this soil mass. So, it will give you a resistance. So, that we have to check that pull out resistance, what is the amount of pull out resistance that we are getting. So, that means we will get a resistance. So, how we are getting the resistance? We are getting because this portion will act as an anchor, and so that this resistance will get in between the friction between soil and the reinforcement. So, that is why this additional length is required. If you do not provide this additional length, because then you will not get that resistance, because only the failure mass it will fail, but the length beyond the failure mass, this LE is the length beyond the failure mass, that will give you the resistance. So, that is why that length is called anchorage length, LE. So, that means we have to calculate separately LR and LE. Now, in this type of retaining wall, LE cannot be less than 1 meter. So, it is must. If your LE is coming less than 1 meter, you have to provide 1 meter at least, this LE. Okay. Another thing is the L0. You can see what is the L0. L0 is the fold portion. Clear? L0 also is equal to actually LE divided by 2, but cannot be less than 1 meter. For example, if your LE is 2 meters say, or 3 meter LE, then your L0 will be 3 meter divided by 2 meter, 1.5 meter, fine. But if your LE is say 1 meter, then L0 is coming out to be 0.5 meter, but no, in that case L0 will be also 1 meter. Clear? So, that means here these are the loads, or this is the lateral earth pressure under which the design can be done, and these are the conditions. So, what we will calculate for this vegetated steep slope retaining wall, we will calculate LR and LE, we will calculate SB. SB is what? Spacing between the reinforcement. Then based on that, we will calculate the number of reinforcement layer, and we will calculate the LE, L0 also, and L0 is very simple, it is LE by 2. Clear? So, now I can, so I am giving a general design procedure, but if you are designing as for any code, then you have to follow their codal provision, remember that. So, I am not here designing for any particular code, I am just designing it for a general purpose. So, I mean in code there are some minor changes are there, but most of the basic things I will discuss, that is the main methodology, but as per if I using any codes, then you have to follow that codal provisions also. Another thing, this failure surface thing, this failure surface that can be not always triangular. It is this planar, this type of failure surface, Suppose if this is the failure surface, this type of failure surface that we have discussed, that is shown here, that is 45 degree plus phi by 2. If this is the h of the height of the wall, then this is applicable for extensible reinforcement. Okay. And for inextensible reinforcement, your failure pattern will be, this failure wedge pattern will be something like this. Okay. So, this one is h by 2, this one is h by 2. And this height, this extension of this failure zone is 0.3 h. So, it's very simple, you take a 0.3 h and then draw a line up to h by 2, then join this point. So, you will get your failure mass. So, this is basically this failure mass, I am talking about this failure mass or failure zone. Okay. So, this is applicable for inextensible reinforcement. What is inextensible reinforcement? Inextensible and extensible means where the reinforcement can extend, and inextensible means it will not extend. So, inextensible reinforcements are, those are very stiff reinforcement, but in the design I will use the geotextile, which is not that stiff. So, it will be treated as a extensible reinforced retaining wall. Clear? So, in the next class, I will start the design methodology, how I will determine the spacing, how we will determine the length. I will discuss that, and then I will solve one numerical problem to show you how I can use those design methodology, and as well as I will do it under seismic and static condition. Thank you.